Swayam Prabha. Digital India. Educated India.
Hello and welcome back to another lecture on control systems. In the last lecture we have seen this interesting concept called joint observability and controllability. Now to be very precise, I have not given you a very rigorous proof of the fact that there are certain structures that always lead to controllable realizations and certain structures that always lead to observable realizations, yeah, and the way I have explained it to you is somewhat intuitive. And it turns out that for the CISO case, this intuition helps us quite a lot. For the MIMO case, we better be a little more careful, but for the CISO case at least, which we deal with in this course, this sort of intuition does a lot to help our understanding or crystallize our understanding of these concepts, right? So I haven't gone to the extent of taking an n cross n controllability matrix or observability matrix and find out what its determinant is and then show you that for different types of structures of the A matrix, what we need for controllability and observability. But what I have just shown you is that if you have any system matrices A, B, C, D, you take the A matrix through a similarity transformation to its Jordan decomposition, Jordan canonical form, which you can always do. Yeah, the diagonal matrix is a special case of the Jordan canonical form. So here's what we have just seen. Let me summarize, recapitulate that. We've seen that if this A matrix is completely diagonalizable, then the first check for you is to see if the eigenvalues of the A matrix of such a diagonalizable A matrix are all distinct. If they are not all distinct, then both controllability and observability go out for a toss. On the other hand, if all the eigenvalues are distinct, then you turn your attention turn by turn to the B matrix and the C matrix. Look at the B matrix entries. If all those entries are non-zero, yeah, then you can say that the realization is controllable. Yeah, so not only is that diagonalized realization controllable, but because this controllability and observability are invariant to similarity transformation, therefore the original realization from which you transform to this diagonal form through a similarity transformation is also controllable. Yeah, so therefore instead of always evaluating this controllability matrix, what we can do is we can get to this Jordan form, yeah, and look at the structure of the ABC matrices taken apart in an isolated fashion. Similarly with the C matrix, for this diagonalizable A matrix, we look at the C matrix for the diagonalized form, and if each of the entries of the C matrix, that row vector, is non-zero, then it's observable. If both B and C matrices have all their entries non-zero and all the eigenvalues of the diagonalizable matrix are distinct, then it's both observable and controllable. In other words, jointly observable and controllable. Then we went on to look at some other structures of this that appear in this Jordan block form. One is this type of Jordan chain of different sizes. So you can have multiple chains for the same eigenvalue, by the way. It's not necessary that for the same eigenvalue lambda 1 you have a size 3 chain and that's it. You can have a size 3 chain, a size 5 chain for a total of 8 by 8 block. Yeah, but anyway, those are details of Jordan canonical form. I urge you to read up a little more on it if you're interested, or otherwise you can take my word for it. But the point is that you see, for each of those chains, not necessarily for each of those repetitions of eigenvalues, for each of those Jordan chains that you have, for controllability you need the last entry, the conformally in the B matrix you look, and that particular entry for the last entry of the Jordan chain, yeah, that particular entry of the B matrix better be non-zero. For the C matrix, the first entry of that chain, that first state, it better make its appearance in the output for it to be observable. yeah. Then we had this complex conjugate eigenvalues which appear as real Jordan block, yeah, block diagonal, and there we saw that any one of the two entries of C corresponding to those two states and any one of the two entries of B corresponding to those two states, if they are non-zero, yeah, it's going to be observable and controllable respectively. Then you can also have repetitions of that complex conjugate eigenvalues, yeah, in which case again the same notion holds as for the real eigenvalues, except that instead of just at one location you check any of the last two locations in the B matrix for controllability, and you check any one of the first two locations, yeah, in the C matrix to be non-zero for observability, yeah. So if you have performed all these checks, yeah, then you don't need to evaluate the controllability matrix or the observability matrix. Just by looking at the structure of the A, B and C matrices, you can say whether it's controllable, whether it's observable, whether it's only one of them or none of them, or whether it's both of them, in which case we call it jointly controllable and observable. Now we will see that this joint controllability and observability is actually something that's also similar to this notion called minimality. What is minimality? So we need to define that first. Again, I will not go into a rigorous definition of minimality. For CISO it's very obvious what I mean by that. So suppose you have GS is equal to NS upon DS, yeah, then the GCD or the greatest common divisor. So remember these are polynomials, right? So this is a polynomial and this is a polynomial. So this is middle school algebra that you've learned, right? How to take the common factors of two polynomials, yeah? Divide one by the other and see how many terms cancel out, yeah? So that the GCD of NS and DS is 1. So in that case they are irreducible, yeah. So if the GCD is 1, then that is the definition of minimality of this CISO transfer function, right. So in other words, we are saying that if we start from this ODE or its corresponding transfer function, and if this transfer function is minimal, yeah, then we will see that any realization of this transfer function is going to be both observable and controllable, and therefore we have a way of going from any one realization to any other through a similarity transformation, yeah. So that will answer the complete question that we posed several lectures back, and today we will wind up with that question, right, that this is what it takes. If you start with a transfer function which has no redundancy, by which I mean that no poles and zeros are cancelling, yeah, it's a minimal realization, yeah. So if you take the minimum number of integrators, it is redundancy free, right. If you are realizing a transfer function using the minimum number of integrators that are required, then and only then the system is going to be both observable and controllable, okay. So let us work our way around both ways. So first, now what I am going to do is I am going to recall something that we did a few lectures back. Now suppose a realization A1, B1, C1, D1. So again we are talking only about CISO, right, so it makes our life a lot easier. So A1, B1, C1, D1 is minimal, or sorry, rather let me assume is jointly controllable and observable, yeah. So it's both observable and controllable, okay, right. We are claim that A1, B1, C1, D1 is a, of course there can be plenty of minimal realizations, no, we can take a similarity transformation and go to, so it's no point in saying is the minimal realization, yeah, there can be infinitely many realizations, we have seen that through similarity transformation, yeah. So A is a minimal realization, okay. So this is our claim that we now want to prove. So in other words, we want to see that joint controllability and observability leads to minimality. So let us say suppose not, So we are going to see some sort of a sketch of a proof. Suppose not. So what does it mean to say that this ABCD is not a minimal realization, this A1, B1, C1, D1? It means that there exists A2, so this A1, let us say it belongs to size n cross n, okay. So it means that there exists A2 belonging to size n bar cross n bar, B2 belonging to size n bar cross 1, C2 belonging to size 1 cross n bar, and of course D2 just a real number in our case, such that A2, B2, C2, D2 is also a realization of the same transfer function, and n bar is less than n, strictly less than n. So in that case it would have been violated, right, because then it means that you can realize the same transfer function using a smaller size, smaller number of states. So that means the characteristic polynomial of A2 will be of n bar degree. If the characteristic polynomial of A2 is of degree n bar and n bar is less than n, then the number of poles of the transfer function is n bar in the second realization, and in the first realization it is n. So that means in the first realization you had some redundant poles which could have been cancelled with some zeros, right. So, so this at least establishes that the way we are heading forward, yeah, we have to rule out this possibility, right. So we have to contradict this somehow. So we are first assuming that this claim is refuted, that a jointly controllable and observable realization may not be minimal. That is what we are trying to posit now, yeah, but now we will shortly see that this cannot be true. So recall this, there is a reason why we derived all these results a few lectures back, okay, we have all got all the tools in our toolkit now. So recall that since A1, B1, C1, D1, irrespective of the size of the ABCD matrix, this is why I was so keen on ensuring this, right, and A2, B2, C2, D2 are realizations of the same transfer function, realizations of the same transfer function. Therefore, we have D1 is equal to D2, yeah, this we have already established earlier, right, through that impulse response, you remember. And furthermore we saw that we must have C1 A1 to the power k B1 is equal to C2 A2 to the power k B2. In between we had another step, if you recall, we had C1 e to the power A1t B1 is equal to C2 a to the power A2t B2, from which we then derived this as a corollary. Please go back, if you do not recall that, go back to that earlier lecture where we have established this for all k that are positive real numbers, yeah, or maybe even, yeah, you can even have this at k is equal to 0, yeah, alright. Now this is true irrespective of the size of A and A1 and A2, right, we proved this earlier. Now consider the product observability of A1 C1 times the controllability matrix of A1 B1, yeah. What does this tell us? This means it is C1 C1 A1 dot 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 till C1 A1 to the power n minus 1, and what is this excuse me, what is this controllability matrix? It is B1 A1 B1 till A1 to the power n minus 1 B1. So what does this matrix look like? You see this matrix looks like C1 B1, of course C1 is a column, is a row, so all of these are rows and these are all columns, yeah. So of course this row times this column is a scalar, right. So then we have C1 A1 B1, similarly you have C1 A1 B1 here, yeah. So all of these entries, if you look at the last entry for example, is C1 A1 to the power n minus 1 B1 like this, yeah, and then you have C1 A1 to the power n minus 1 B1 here, and likewise if you go, this is of course C1 A1 squared B1 here like this, till the last one if you go, it is C1 A1 to the power 2n minus 2 times B1, right? You agree? Yeah, there is nothing to disagree here with this. This is C1 A1 to the power n B1. Yeah. So now I am going to make a claim here. Look, look at this matrix here. Yeah. What is the size of this matrix? This is n, this is n, this is also n, yeah, this is also n. Although I have written it, drawn it in this fashion, like one looks tall, one looks short or wide, yeah, both they are both n cross n matrices. And now if both of them are invertible, yeah, then clearly O1 inverse, so let me call this O1 by the way, yeah, so O1 C1. So O1 inverse and C1 inverse exist, right? They clearly do. So therefore, C1 inverse O1 inverse is an inverse for O1 C1. That is the matrix we have just written here. Yeah, this is the matrix we have just written here. But now I am going to use this fact, and I am going to replace each of those this A1s. Yeah, I am going to replace each of them, A1 B1 C1. Yeah, I am going to replace them with C2 B2 C2 A2 B2 likewise. Yeah, so therefore it means that this matrix C2 B2 likewise till C2 A to the n minus 1 B2. Remember, this is not just true for k up to some number n or n bar, this is true for all positive integers till infinity, right. So therefore, even though the size of this C2 B2 A2 is like n bar or n bar cross n bar, yeah, we can still say that well, I can raise this to any power. This A I can raise to any power. The A2 might be of size n bar, but I can still raise it to the power n minus 1. So therefore, I am just going to replace this using this result here. So this is going to be C2 A2 B2. Likewise, let me just take a look. C2 A2 to the, yeah, C2 A2 to the power n minus 1 B2. Likewise, still C2 A2 to the power 2n minus 2 B2. Okay. So this is equal to nothing but O1 C1. Yeah. But this is equal to what? You see this, if I write the observability and controllability in terms of O2 C2, that will be of a smaller size, right. So what I am going to do is, I am going to take this, this is nothing but, if I write the O2 matrix here, yeah, if I write this O2 matrix here and I pad it further with additional terms here, that is C A to the n bar, then C2 A2 to the n bar, C2 A2 to the power n bar plus 1 likewise till C2 A2 to the power n minus 1. Yeah. So remember, till here this is of size n bar, yeah, this is also of size n bar, right. So now you note that this is of size what, and look at the other thing here, this controllability matrix here, yeah. So this I can write this controllability 2, So notice look at the size of this now, yeah, this is of size n bar, correct. Now this is of size n bar, and okay, this is of size how much, this is of size n minus n bar, yeah, this many additional rows I have entered. Here also I need to do the same thing, no, because this is of size n bar, this C2 matrix, the controllability matrix here is of size n bar. So I need to add further n minus n bar. So here I am going to add this a2 to the power n bar b dot 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 till the last one will be a2 to the power n minus 1 b, right. That is what this is, you can check, yeah, this is n bar plus 1 so on till n minus 1, so I am just extending it. Now look at these individual matrices, what is the size of this matrix? This matrix belongs to R n cross n bar, yeah, with n greater than n bar, and this matrix belongs to this matrix after this padding, yeah, I have just padded it with some extra rows here, the observability of O2 and the controllability of C2, controllability of realization 2, C2, I have padded with some columns to the right, yeah. So this belongs to now what size? This belongs to n bar cross n, yeah. Now I know that this matrix is non-singular because its inverse exists, yeah, so it is invertible, but that means that this matrix must also be non-singular, right. So therefore this padded matrix, let me use a different color, this whole padded matrix, suppose I call this O bar, and this whole padded C matrix I call this C bar, yeah. So therefore I have my the obvious conclusion that I am led to drawing from here is that O1 C1 is equal to O bar C bar. Now since O1 C1 is invertible, so must be O bar C bar, yeah. So therefore there does not exist any non-zero vector v such that O bar C bar times v is equal to 0. Why? Remember, again, maybe it is a little sophisticated result, but you see what this means. It means that if such a vector, non-zero vector exists which takes this O bar C bar to 0 upon post multiplication, it means, so this v belongs to Rn cross 1, yeah, it would mean that basically it is a linear combination of the columns of this matrix, but this matrix is in turn equal to O1 C1 which is non-singular. So if this matrix is equal to this, then if this is non-singular, then this also has to be non-singular. If this has to be non-singular, it means its columns are linearly independent, which means that there does not exist a non-zero combination of the columns, a non-trivial combination of the columns of this matrix that results in 0, yeah. But on the other hand, you look at this matrix C bar, look at C bar, what is the size of C bar? C bar has n bar rows and n columns, yeah. C bar is a so called wide matrix, yeah, that means more columns than rows. So again, excuse me if I am using a bit of linear algebraic result here, but what I am saying is essentially that if a matrix is a wide matrix, yeah, then it cannot have full column rank because it has more columns than the number of rows, and the rank of a matrix, whether it is the row rank or column rank, is the same thing. This is a result I am using from linear algebra very loosely. I hope you can excuse me for this usage without explanation. Rank of a matrix can at most be equal to the lower of the number of columns or the number of rows, right, because the column rank and the row rank of a matrix are the same. A very kind of a funny kind of a result, right, it requires a bit of linear algebraic proof, we will not get into that, but the point is that the rank of this matrix can at most be equal to n bar, yeah, because n bar is less than n and n bar is equal to the number of rows. So it can at most have full row rank, it cannot have full column rank, yeah. So therefore columns of C bar cannot be linearly independent. That means there exists V such that CV, so V belongs to what? Rn, such that CV is equal to 0, C bar V is equal to 0. That means once C bar V is equal to 0, I will have that O bar C bar V is equal to 0. But that means because O bar C bar is equal to, remember, O1 C1 is equal to 0, 1 C1 V is equal to 0. But that would mean that O1 C1 is singular, which is clearly a contradiction, no, because I know that O is individually, O1 and C1 are individually invertible. So therefore O1 C1 must be non-singular. If O1 C1 must be non-singular, then O bar C bar has to be non-singular. But this is telling me that if the size of my A2 matrix and B2 matrix and C2 matrix, they are smaller than the corresponding sizes of A1, B1, C1 matrices, then this is exactly the situation I will land up with. So therefore this is a contradiction. So let me write it in red, hence the desired contradiction. So what have I proved? I have proved that if you have a realization that is jointly controllable and observable, then it must be minimal. You cannot have a realization of a size smaller than that, okay. So basically joint controllability and observability leads to minimality, yeah. So now the other way around, if a realization has to be minimal, must it then be controllable and observable, yeah. So what do we need to show that, in order to prove that? In order to prove that, we need to show that suppose the realization is minimal. So if a realization is minimal, so this we have already shown, hence joint controllability plus observability leads to minimality, okay. This part is done. Now to show that, and this will require some understanding of the Jordan form, again we will revert to that Jordan form, okay. But hopefully by now you have already revised the Jordan form a bit, so you will be in a better shape to appreciate this, okay. Now we have to show that minimality implies that the realization must be jointly controllable and observable, yeah. So remember, this minimality is a notion that can be checked in the transfer function domain, that is the beauty of it, okay. So we have related a property from the transfer function domain, the classical domain, to this joint controllability and observability property in the state space domain. Who knew that could be possible, right? Because remember, when we started to look at this controllability and observability property, our prime motivation apparently was this, this idea of being able to simulate a differential equation in this analog computer, right. That apparently led to this idea of controllability and observability, and then we saw the idea of state observability and state controllability, right. So on the face of it, there is no connection between this and some transfer function domain notion, right. But it turns out that this is why it is so beautiful, because now this minimality you can check in the transfer function domain. If you check the numerator and denominator polynomials and check their GCD, the greatest common divisor, if that greatest common divisor is unity, yeah, then you would know, or yeah, then you would know that any realization you get to in the state space domain will be jointly controllable and observable, right. So that is a beautiful thing, right. And now we are trying to see that if you come up with different jointly controllable and observable realizations, yeah, that, or rather if you come up with a minimal transfer function, then from it whatever you derive, you will get that realization as jointly controllable and observable. Sorry, we have not proved it yet, we are yet to prove it. So what we have proved now is that if a state space realization is jointly controllable and observable, yeah, then you are basically using the minimum number of integrators that you absolutely need, nothing is redundant. So now we will see the other way around again. So this is a reprise. We go to that Jordan block form. So this, I am not going to use this diagonal, D as a diagonal form, yeah. Then this J I am going to use as a Jordan chain for the real Jordan chain, so the JR. Then I am going to use this JC for the complex Jordan chain, so this is the diagonal real. Then I am going to have diagonal complex block, yeah, what by that I mean this blocks like this A minus B, B, or AB minus BA, whichever way you like, it is a matter of taste, yeah. Of course this, so this is basically this same block sitting here and some identity being padded on here, right, that is this block, yeah. This JR of course I understand is lambda, lambda, something like this lambda, and with 1s on the super diagonals. This D of course I understand is lambda 1, lambda 2, like this lambda n, right. So I have all of these different structures that are sitting here, right. So the last I can have like maybe multiple DCs like this, yeah. Now we are not looking at the joint controllability and observability, but minimality. So if we find now that for minimality, yeah, we need exactly the same conditions that we had earlier established for joint controllability and observability in the previous lecture, then we are done. I repeat, now from the same Jordan block, because we knew that in terms of the Jordan block what the condition for minimality or rather what the condition for joint controllability and observability were. So now if we can relate the same Jordan block realization with some equivalent condition for minimality, and then in turn prove that those conditions are exactly the same conditions that were necessary for joint controllability and observability, then we are done, okay. So this is a typical A matrix when transformed into its Jordan block form. Now let us look at the B matrix, which is some sort of beta 1, beta 2 like this, and let us look at the C matrix, which is some gamma 1 dot 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 till gamma n, okay, fine, we are good to go. Now I am going to again ask you to extend your imagination a bit, not just imagination necessarily, you actually have the luxury of sort of taking a piece of pen and paper and trying to work it out, but you see that if you take this e to the at in this Jordan form, yeah, each of those forms we know what they look like, right. So let me try to tell you what this form will look like. So this first block is just going to be those e to the lambda t's, no, so it is going to be like e to the dr t, yeah. We know that this is like if you have a diagonal matrix lambda 1, lambda 2 like this till lambda n, then it's e to the this t is going to be e to the lambda 1 t dot 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 till e to the lambda n t, yeah. So that is what I mean by this, okay. What about the second type of block here, this Jordan chain? You see this Jordan chain, again it requires a bit of work, but I hope you will be doing this work, yeah. So this Jordan chain will look something like this, yeah, e to the power this lambda lambda dot 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 lambda 1 1 1 t is going to look something like e to the lambda t dot 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 till e to the lambda t as usual in the diagonals. Then you see in the first off diagonal you have t to the lambda t, yeah, all t to the lambda t. Then in the next one you will have t squared by factorial t lambda t, right. So if this is of a size k cross k, yeah, then in the last entry here you will have t to the k minus 1 by factorial k minus 1 e to the lambda t, yeah. This is what this chain looks like, please verify, okay. This is what this e to the jrt will look like, okay. What does this complex chain look like? So e to the, what I have then is this sort of block diagonals and identity, and this identity and this block diagonal, yeah, these are all 2 by 2 blocks, remember, these are all complex conjugate eigenvalues. So this you can again verify will look something like e to the at, some matrix here, e to the at, some matrix here, I am going to shortly tell you what that matrix is, e to the at, some matrix here. So that matrix is going to look like cos b, sin b, minus sin B cos B. Yeah, that is what each of those individual matrices are. Yeah. Additionally, you will have t e to the at and then that matrix. Here you will have t squared by factorial 2 e to the at and then that matrix. Yeah. Likewise, here you will have t e to the power at this matrix. Okay. So if this is a 3 by 3 size, then maximum power you will have t squared. Yeah. What about the other block? Of course, we have now covered everything, right? So if you have just the diagonal this chain, so this is, let us say, this e to the, this is not diagonal, I am sorry, what did I name it? JC, the complex Jordan. Yeah. So e to the JC, so e to the JCT. Yeah. So this JCT will look something like this. This will be sitting here, right? So again, you see what this looks like. And finally, of course, if you have just e to the dt, it's a small easy case, e to the dct. Yeah, the complex diagonal form, block diagonal form, that will of course just look like e to the at cos bt. Sorry, this is t, I missed the t here. Yeah, cos bt minus sin bt cos bt. Yeah. So this is going to be this block. So each of those blocks in the e to the power at format, I know what they look like. Now what I am going to do is, I am going to take Laplace transform of this e to the at. Okay. So please pause here if you want and write this down, note this down, and convince yourself that indeed I am not sort of glossing over this, and that each of these forms here in the Jordan form, from this a, if you want to go to e to the at, then each of those individual blocks, they actually look like this. Yeah, just convince yourself that I am not sort of glossing over this and not just hand waving this. Okay, if you want to prove this, if you want to check this, you can always prove. We have already discussed about the Jordan form and shown you how to take the exponentiation, matrix exponentiation under the Jordan transformation. We have discussed that several lectures back when we discussed stability, as a matter of fact. But the payoff is here, and that is why I wanted to really discuss Jordan form, because in the end it really sort of is very handy in not just analyzing what we have done so far, but also in what we are doing currently, right? Not just about stability. Yeah, it is also telling you about these beautiful properties like controllability, observability, minimality, so on and so forth, right? Okay. So now having convinced ourselves of this, let us look at this. So what do we have here? Now it looks like a bit of mental gymnastics to start with, but if you just go through very slowly and carefully, you will see this is exactly what it is. What is the Laplace transform of this? Now I am going to take the Laplace transform of this, I am going to take the Laplace transform of this, I am going to take the Laplace transform of this and this and this, all of them, right? So I am going to take the Laplace transform of each one of these types. So this is one category, this is one category, this is one category, what else? Yeah, and this is another category. So these 4 types of blocks are what we encounter, right? Real diagonal repeated. Yeah. So we are going to come up with this, right? Now let us see what happens. So suppose we have the first type of block, which is just the diagonal. So we have e to the lambda 1 t dot 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 till e to the lambda n t. Yeah. So if we take the Laplace of this, what do we get? We get s minus lambda 1 dot 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 till 1 by s minus lambda n. Likewise, right? Notice that now this is Si minus A inverse, right? Why we are doing this is because this is Si minus A inverse. Now if we pre-multiply this by C and post-multiply this by B, what we get is actually the transfer function, right? So from a, sorry, this, let us not call this N, let us call this K. So from a K by K size matrix, yeah, if it is irreducible, if it is a minimal realization, I must have a kth order denominator polynomial. Yeah, I must have a kth order denominator polynomial. But notice what is this turning out to be? this will turn out to be summation. So if C's are like gamma 1, gamma 2 like this till gamma n, again check, and these B's are like beta 1, beta 2 like this till beta n, then this is nothing but gamma I beta I by S minus lambda I, summation I is equal to 1 to k. Now if any one of those lambda i's happen to be 0, any one of those gamma i's happens to be 0, what happens? You are basically going to miss out on that term, that particular lambda I term. So you will be left with k minus 1 terms. So if you take the LCM of k minus 1 first order factors, the denominator polynomial will be of degree k minus 1. So therefore, if you now go back to that big matrix here from this diagonal block here, what does it entail? It exactly entails that if any one of those B's or C's entries for this, for this first k entries of B or the first k entries of C, if any one of them is 0, then you will be missing out that particular mode from the transfer function, and therefore this k cross k block, this determinant. So note that this is, since it's a block diagonal form, the determinant is just the product of these determinants, individual determinants. No? So this part of the determinant, which is k cross k block, will give me a denominator which is of degree less than k. So that means that this is exactly the condition for joint controllability and observability, that all these gammas and betas must not be equal to 0, right, in the diagonal case, right. And you see now that if any one of those gammas or betas are equal to 0, not only do you lose either controllability or observability, but you also lose minimality, because then this matrix, the total degree of this is less than k minus 1. So no matter what the degrees of these other blocks are, the overall degree of this denominator polynomial cannot be equal to n. If this A is of size n cross n, then already this part is yielding a denominator polynomial of degree k minus 1. So this part can at most yield a degree equal to its size, this part can also yield equal to its size. So you are already deficient by 1 here. So you've seen that one part of this loss of controllability and observability, that is either of those gammas or betas being equal to 0, translates beautifully into lack of minimality. What about the other part? What if any two of these eigenvalues are identical? We've seen that that also causes you to lose not just observability or controllability, but both observability and controllability. So what happens if any of these lambda i's are identical? Well, again, you can then write, suppose without loss of generality, lambda 1 is equal to lambda 2. Then what you have is gamma 1 beta 1 by s minus lambda 1 plus gamma 2 beta 2 upon s minus lambda 2, which is going to be nothing but some gamma 1 beta 1 plus gamma 2 beta 2, which is a constant, by just s minus lambda 2 or s minus lambda 1. So therefore you have a sum of less than, effectively sum of less than k first order factors, right. If any of those two eigenvalues are identical, then you again end up with a sum of these rational functions, each of which is a first order polynomial in the denominator, and you have how many of them? Less than k of them. And again, this is a condition that was exactly the same for loss of controllability and observability, and you see here it also leads to loss of minimality, because now again this leads to the conclusion that this block will generate a denominator polynomial of degree less than k, even though the size of the block is k. Now again you look at the second block here, it's beautiful. Now look at the second block here. What happens here? You see this last entry has the highest power of k, and if you take its Laplace transform, this will give you the highest degree denominator, because every time you recall this, that if you take t times ft or t to the power k times ft, and if you take its Laplace transform, this is just going to give you the derivative, right. You take the derivative as many times of this fs, right, with a minus 1 to the power k, of course. So if you have ft's Laplace transform is equal to some 1 by s minus a, which is clearly the case here, this e to the at, it has e to the lambda t, it has s minus lambda in fact, then this t to the power k minus 1, you will differentiate this k minus 1 times, so therefore you will get this will have some polynomial s minus lambda to the power k, yeah. Now note that if this is a block of size k, or rather maybe call it k1, k2, so this is k1, this is of k2, so let us say this is of size, where was I, yeah, so let us say this is of size k2, yeah. So the only way, now notice that if you take this fellow's Laplace transform, so take the Laplace transform of e to the lambda t dot 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 till e to the lambda t, yeah, and you have t to the k minus 1 by factorial k e to the lambda t. Every other fellow here has a degree of this t less than k minus 1, so only this fellow will eventually, after Laplace transform by factorial k e to the lambda t, only this fellow in the whole matrix e to the lambda t, which is basically, now if you take the Laplace transform, it is Si minus A inverse, yeah, the only this fellow, this 1 comma k, k2, yeah, so this is let us say k2 cross k2, yeah, so this 1 comma k2 entry, 1 comma k2th entry, only this fellow leads to a Laplace transform that has exactly the desired number of desired degree in the denominator polynomial, yeah. Any other fellow that you pick up will not ever be able to give you, so some coefficient, I do not know, gamma, alpha, whatever, alpha, beta, whatever, yeah, some alpha times this will come eventually. So you must pick this fellow. So when you pick this C and B, when you pre-multiply by C and post-multiply by B here, you have to pick out this fellow. So that means, what does C do? C picks up a certain row of the Si minus A inverse matrix, B picks up a certain column of the Si minus A inverse matrix. So C must pick out the first row of the Si minus A inverse matrix, and B must pick out the last column of the Si minus A inverse matrix. But what does that mean? That C must have a non-zero entry in its first position and B must have a non-zero entry in its last position. What does that remind us of? That reminds us of the exact same condition we had for joint observability and controllability, right? So we have put a check, we have verified that for this block the conditions for joint observability and controllability, yeah, need to be satisfied in order for it to be minimal, yeah. So if you are realizing it in the minimal fashion, it must be jointly controllable and observable. For this block also we have now checked that if you realize, if you want this to be minimal, then it must be jointly controllable and observable. Now for the third block, this complex block, again I leave it to you, now you check, instead of just the one block you will now have a 2 by 2 block. So what sort of realizations do you get here? If you see, you will get this e to the at and then that cos sine minus sine cos type of matrix, e to the at, then this cos sine minus sine cos matrix, and e to the power at cos sine minus sine matrix. Then you have t e to the at and that same matrix. Here also you have t e to the power at and the same matrix. Once again you see the highest power of t appears only in the last 2 by 2 block. That is, if you pick any of these last 4 blocks, yeah, if you pick any of these last 4, not blocks, any of these last 4 entries, so this is basically my e to the 8, this exponential for this part, right. So if I take the Laplace transform of this, I will get the Si minus dc, what did I call it, let me see, I have not been very precise with the notation, excuse me for that. So this is the d complex, right, this inverse, yeah. Now if I hit it with the C and B from here, what do I basically need from my C and B in order for this to be minimal? I need that the C must pick out any one of the first 2 rows, yeah, and the B must pick out any one of the last 2 columns, yeah, it has to pick out, right, otherwise it's just not done, no, it has to pick out either the first 2 rows have to be picked up by C, or and the last one of the last 2 columns have to be picked up. So the C structure, either this, not that, this is the B structure. So the B structure, either this or this. So this is the n minus k3 minus 1th entry and the k3th entry. This is the B matrix, and the C matrix structure better have the first or the second entry. Yeah, any one of this is an OR, not AND, this is an OR condition, yeah. Only then will I have the highest degree term appearing. In this case it is t squared, it could be any higher degree, right, this is the structure, right, all this will be 0. So this is again the same condition that we arrived at for joint controllability and observability. So for all these 3 blocks successively we have checked now, yeah, that if you want to get the highest degree in the denominator, which is equal to the size of the block itself, yeah, which is basically what you need for minimality, then you better satisfy the condition for joint controllability and observability. And finally the last block here, you check, it's again going to be the same, it's just something like this, right. So again, if you don't pick out any one of these 2 blocks, so you either have to have 1 in any of these for the B matrix, or you have to have a 1 in any of these for the, and you have to have one in these for the C matrix. If you miss out on both, if you don't have a, if you have a 0 entry on both these positions for the C matrix, and you have a 0 entry for both, or you have a 0 entry for both these positions of the B matrix, you either miss out on observability or controllability respectively, yeah. So which is again the same as the condition for joint controllability and observability, right. So then what we then see is, okay, let me just write that down, since let me not be a little lazy here, let me complete the story here. So then you have this e to the at cos bt minus sin bt minus sin bt cos bt, yeah. So this, if you want to take now the sorry, what was that, yeah, so this, if you now want to take the si minus a inverse, the Laplace of, we take the Laplace of this is going to give you like the second degree polynomials, I don't know, b squared or whatever b, but this is going to be some s squared plus something, right. So this is again b squared by s squared. So if you don't pick out any of these 4 fellows, yeah, from here, from this block, then you will be missing out not just 1 degree, but you will be missing out 2 modes at the same time, right. But if you pick out any one of them on the other hand, then you will have some hope of carrying out this, right, or carrying forward this 2 degree, the second degree denominator from this 2 by 2 block, right. Now by the same token, again you note that as we've done earlier, yeah, this the same argument for all these blocks now that we have seen, that the condition for minimality. So how did we approach this? To summarize, we looked at the e to the at matrix in the Jordan canonical form. We saw that there are certain ways in which they might appear. The key to understanding this is what the Jordan block looks like in the upon matrix exponentiation. So upon matrix exponentiation, we saw that the Jordan block has this upper triangular structure, yeah, in which the one and the entry at the right corner, the top corner, or the northeastern corner if you like, yeah, the entry in the northeastern corner must be picked, yeah, because that actually gives you the highest degree. Of course if it is just a diagonal part, then you have to pick each and every one of them, which is again identical, and those eigenvalues better be non-identical, yeah. So that is again the same condition as joint controllability observability. If it is a Jordan chain for real numbers, you have to pick the northeast entry, the top right corner, yeah. If it is the complex conjugate fellow, then you have to again have one of the b's and one of the c's, yeah, one of the 2 c's or one of the 2 b's for those blocks better be at least non-zero, yeah, for them to make an appearance. Otherwise you will be missing out on that second degree factor altogether from the 2 by 2 block, and hence your realization will not be minimal, because your overall transfer function will have a degree which is less than n, right. And then we looked at the Jordan block for the complex conjugate, the real Jordan block for the complex conjugate eigenvalues, and there also we deduce the same thing, right. So in all of these cases the Jordan block, that is why I say the Jordan block is the most powerful, one of the most powerful tools for square matrices, right, because every square matrix has this Jordan decomposition. So almost any proof of that uses matrices, you go to the Jordan block and you will find some way or the other to prove that result, right. So then what we have seen is that the conditions, so let me summarize it here, all conditions for minimality are identical with the conditions for joint controllability and observability. Therefore, minimality will imply joint controllability and observability. So of course now you might say that, well, what is the guarantee that you might have picked this last fellow, but they might have cancelled each other out in some weird way or the other, right? So what is the proof? But remember, we already proved that earlier. We started this lecture with the proof that if you have a jointly controllable and observable realization, yeah, we use that older result, that CA to the power IB, CA to the power KB in one realization must be equal to CA to the power KB in another realization, irrespective of the size of the two realizations, right? So we assume that some realization is jointly controllable and observable, and then we assumed that there exists another realization of a smaller size which is leading you to the same transfer function. In other words, this jointly controllable and observable realization fails to be minimal, and then we showed the contradiction. So earlier we have already seen that joint controllability and observability is the same as minimality in the transfer function domain, and now we have seen that minimality, if you have to meet minimality conditions in the transfer function domain, then you better have joint observability and controllability in the state space domain. So therefore those two notions are very much the same. One is in the transfer function domain, one is in the state space domain, right? So we have arrived at this equivalency between this property in the classical control domain and this property in the modern control domain, right? So hopefully you found this bit of, although it required a bit of tabulation and bookkeeping, and at some times you might have felt it's a little laborious, but I hope that when you have more time at your disposal and you take an exercise book and a pen and try to work this all out, yeah, try to write this out in detail to satisfy yourself, to convince yourself that indeed what I am claiming here is not just some hand waving facts, but you put together every piece we have discussed so far, which is to say that you go back to those matrix exponentials for the Jordan form, yeah, and then you put them those pieces together, and you'll see all of this fitting in, coming together very nicely, yeah. So an idea in transfer function domain is equivalent to another idea in the state space domain, and this connection is something that's a recurrent theme that we always try to see in going from this classical approach to this modern control theoretic approach. So the next few lectures, whatever is remaining of this course, we shall actually talk about synthesis. You recall in our discussions related to what should I say, the classical control part, we had one analysis part, and then finally we ended with synthesis, right? We showed you how to design controllers using root locus in some detail. Of course we didn't discuss the root locus, the controller design technique using Bode plots and other such tools, but they do exist. But here we shall now show you a drastically different method of designing controllers in the state space domain. To motivate that, here's some food for thought, so keep thinking on this before we meet next. So suppose you have a transfer function, we'll revisit this in the next lecture in some detail. Suppose you have a transfer functions, say such as this, okay, s minus 1, s plus 5, s plus 4, okay. So this is suppose my g of s. So then my root locus, so you see then my root locus would look something like this, that I have a pole here, or let me actually have a 0 at the origin itself, right, and a 0 here, right, and then I have another pole at minus 4 and minus 5. Now clearly then the root locus of this fellow will look something like this, yeah, and then of course there will be some breakaway point here between these two poles, right, and then what happens? Well, these breakaway, and where is the asymptote? So this is minus 1, so this is 1 minus 5 minus 4, that's minus 8 by 2, so that's minus 4. So I think it will be near minus 4 if I am not mistaken. So basically you then have this asymptote, yeah, we have this asymptote along this, yeah, if my calculations are not off, then this is how this root locus would look. So now notice that if you just use a proportional controller here, one branch of the root locus is always going to be in the RHP, yeah, one branch of the root locus is always going to be in the RHP. You cannot even stabilize this, forget about performance. What if you use some PD controller, yeah, which is in some way at least sort of less restrictive than sort of the lead compensator, right? So it's just a 0. So no matter where you place the 0, yeah, this branch is always going to be unaffected. No, there's always going to be some part of this part of the root locus which you can do nothing about, yeah. So the P or PD fails to stabilize this plant, and that is primarily because we know from this root locus there's only so much we can do. Not just that, if you have actually practiced some of those root locus design problems, you would have noticed that there was a bit of trial and error involved, right? Because we said that, well, approximate cancellation of the pole and 0, right? Yeah, and then we said, well, we have to simulate and then check if the performance is as desired, yeah, and then if it is like, well, we might feel that it's approximately cancelling out, but as a matter of fact it may not cancel out as well as we want it to. So then again we start from scratch, and it's a bit of an art after a point, right? Even though it involves a lot of calculations, but it's a bit of an art to be able to design these pole 0 locations of the lead or lag compensators at some level, no? So if I give you some such typical plant, you might find it inordinately difficult to have a satisfactory behavior as well as steady state error and things like that, yeah. So that was one restriction, it was laborious, right? Now what using the state space method we shall see is that subject to certain restrictions and conditions, yeah, and those conditions will exactly be boiling down to this joint controllability and observability, yeah, I can place the poles anywhere I like. In fact, if I just have controllability and I have access to the states, we will discuss more of this in the next lecture, of course, but if I just have access to the states, I can actually place my poles anywhere in this complex plane that I like, okay. I have no such restrictions of where I can place the poles. This is one of the greatest triumphs of this modern control theoretic approaches, right? It's beautiful, and once you sort of see how beautifully it works, how elegantly it works without having to go for trial and error, you just tell me where you want the poles and I'll tell you what sort of a controller you need in order to place the poles over there. It's just that beautiful, okay. Then you will really fall in love with this method of designing, okay. So that's the promise for the next lecture. We've hopefully been able to motivate to you some lacuna or some drawback of this controller design or synthesis technique in the classical domain. So now in the modern control theoretic approach, we will see how this can be circumvented. In the next lecture we shall start with exactly this same transfer function that I have considered now, yeah, and we'll look at a realization of this in the state space domain. You can clearly see here in this transfer function that this transfer function is minimal. There is no common pole and 0, right? So this will actually allow us to place the poles anywhere we like, okay. So that's a topic or the subject for the next few lectures. Till then, take very good care. Thank you.